Introduction, substitution versus eliminations. What is substitution and elimination reaction? So substitution reaction is one atom or group is replaced by another atom or group, while elimination reaction is atoms or groups are removed to form a double bond, which is alkene. So substitution retains the carbon framework, while elimination changes the structure of forming a pi bond. So here is the difference between SN1, SN2, E1 and E2. As you can see here, SN1 and SN2, the reaction type both are substitution, but for E1 and E2, both reaction types are eliminations. But the number of steps for SN1 is 2 steps, and E1 also 2 steps. But for the S2, the number of steps is 1 step, and also for the E2, 1 step. And then, as you can see there, the nucleophile base or the strength, the SN1 is they have the weak nucleophile, while the SN2 have the strong nucleophile. While E1 they have the weak base, and E2 have the strong base. Role of nucleophile versus base. So nucleophile donates an electron pair to form a new bond with carbon, and they promote substitution reaction SN1 or SN2. And then the base removes a proton, which is H plus from a molecule, and they promote elimination reaction E1 or E2. And the strong nucleophile favors substitution. Strong base favors elimination. Why different mechanism exists? So the reason is different substrate structure have the primary, secondary, and tertiary, and they have strength of nucleophile base, and then the type of solvent used, which is a polar protein or polar aprotate, and the reaction temperature and also the stability of intermediates.
SN1, which is unimolecular substitution reaction, meaning the reaction rate depends only on the substrate concentration. SN1 reaction are multi-step and favor weak nucleophile like water. Bond breaking occurs first to form a carbocation intermediate, then bond forming occurs when a nucleophile attacks. For example, we use water as nucleophile, 2-chloro, 2-methylpropane as substrate, and the leaving group is chloride. In the first step, the carbon-chlorine bond breaks because it's polar. Carbon is partially positive and chlorine is partially negative. Chloride ion leaves, forming a stable tertiary carbocation ion. This step is slow and is a rate determining step. Next, water acting as a weak nucleophile attacks the carbocation ion to form a protonated alcohol. Finally, another water molecule removes a proton from the protonated alcohol, giving a neutral third butyl alcohol product. Because the rate determining step involves only the substrate, the rate law is rate equals K times the substrate concentration. Tertiary alkyl halide react fastest, while secondary reacts slower, and primary and methyl halides rarely undergo SN1.
In an ion elimination reaction, the nucleophile involved is typically a weak base, such as water or alcohol. The general order of reactivity is benzyl halides greater than aldyl halides, followed by tertiary alkyl halides, and then secondary alkyl halides. For primary alkyl halides and methyl halides are unlikely to undergo E1 reaction because the carbocation ion they form are extremely unstable. Move on to mechanism. The carbo-iodide bond breaks heterolytically with iodine leaving as iodide. This produces a tertiary carbocation ion, which is relatively stable due to hyperconjunction and the electron donating effect of the 3 methyl groups. This is a slow step that requires highest activation energy, so it determines the overall reaction rate. After the slow rate determining step forms the tertiary carbocation ion, water acts as a weak base will quickly remove a beta hydrogen from one of the adjacent methyl groups. The electron from the CH bond immediately shifts to form a CC double bond, producing 2-methylpropane and H3O plus as a byproduct.
SN2 reaction is a bimolecular substitution reaction. So it is a one-step reaction and involved in the breaking and the forming of bonds occurs at the same time. So for this reaction, it favors the strong nucleophile. The reactivity order of this reaction is followed by methyl halide and primary alkyl halide and secondary alkyl halide. The methyl halide has a higher reactivity and followed by the primary alkyl halide and secondary alkyl halide. The tertiary alkyl halide do not react with the SN2 reaction because it has a steady hydrogen effect. In this SN2 reaction, the strong nucleophile is hydroxyl ion and the electrophile is bromoethane, and the leaving group will be the bromide ion. The hydroxyl ion will act as a strong nucleophile and it will attack the carbon atom from the opposite of the leaving group, which is bromide ion. The reaction will occur in a single step without the formation of any intermediate compound. So the system will pass through a transition step in which the carbon is partially bond to the nucleophile, which is the hydroxyl group, and also the leaving group, bromide ion. So during this transition step, the bond formation and bond breaking will occur simultaneously. So as a result, the CBr bond will break while a new CO bond will form. This will lead to the formation of ethanol.
The reaction is a bimolecular elimination reaction. It is also a one-step reaction as halide leaving and proton abstraction happen simultaneously without intermediate formation. Now, we will explore the E2 mechanism using 2-bromobutane under 2 different conditions. The first condition is with sodium hydroxide in ethanol. Sodium hydroxide is a strong base which abstracts the more substituted beta hydrogen, causing the formation of carbon-carbon double bond and the breaking of carbon-bromide bond. The leaving group will be bromide ion, which then leads to the formation of SiZ product 2-butene. The second condition is with potassium third butoxide in third butanol. Potassium third butoxide is a bulky strong base which abstracts the less substituted beta hydrogen, causing the formation of carbon-carbon double bond and the breaking of carbon-bromide bond. The leaving group will be the bromide ion, which then leads to the formation of Hofmann product 1-butene.